Good morning. Thank you for attending this session. My name is Trevor Marchand. I'm an emeritus professor of social anthropology at SOAS, University of London, and I thank the organizers for inviting me here to share my learning and thoughts as an anthropologist with a community of archaeologists. My objective in this morning's presentation is to promote the role of hands-on learning in archaeological field methods. This can improve our understanding of past human skills, problem-solving activities, tool use, and the choice of materials that our ancestors made in relation to their given cultural and environmental context. The presentation begins with a brief introduction to my anthropological research with contemporary craftspeople, followed by a longer discussion of an experimental archaeology project headed by Maurizio Tosi and Gregory Postle on the east coast of Oman. I came to social anthropology as a trained architect with considerable experience of construction sites. My move to anthropology was motivated by a keen interest in skill learning and traditional craft knowledge. Anthropological studies with craftspeople took me first to northern Nigeria, then Yemen, afterwards Mali, and more recently to London's East End, where I trained full-time for 2 years as a fine woodworker and furniture maker. For more than a decade, my fieldwork focused on masons operating in cultural contexts where they were properly and popularly acknowledged to be master builders. This means that they were responsible for both design and construction, and they typically operated without the use of measured architectural drawings or any reliance on professional engineers. Their learning was grounded entirely in practical apprenticeships. The masons with whom I worked in West Africa and Arabia were highly practiced in the vernacular styles of architecture that characterize their historical towns and cities. And they employed manual technologies and either sun-dried or kiln-baked bricks to create distinctive building forms and decorative elements. In fieldwork, I use an apprentice-style method. I train and labor over long periods with communities of craftspeople with whom I establish a solid rapport. In this exchange of toil for ethnographic knowledge, my physical contribution of labor offers me privileged access to practices and various expressions of expertise. A regular schedule of long hours and engagement in what are often repetitive manual tasks allows for repeated observation and more detailed understanding of artisanal techniques and of the modes of communication used by craftspeople in their teaching and learning of skills. Apprenticing as a technique of anthropological inquiry is especially well suited to the study of learning and knowing in practical contexts where talking is secondary to doing. It also equips anthropologists with firsthand experience and possibly some level of expertise in the practices that they theorize and write about. While working alongside craftspeople, I could indulge my curiosity about the way that we as humans think, calculate, communicate, and create. In the process, I also gained greater confidence in my own abilities to problem solve within the flow of the task. In the long abstract published in the conference proceedings, I briefly discuss my methods and findings while conducting fieldwork with a specialized team of traditional minaret builders in Yemen's capital, Sana'a. And these are some images of the work that I did in Sana'a. That research was also published as a monograph and in numerous journal essays. Shortly after finishing fieldwork, the political situation and security in Yemen very sadly deteriorated, preempting the current civil war that erupted in 2015 and which continues to menace the future survival of the people and their once spectacular cultural and architectural heritage. In 2000, I began visiting Oman on a regular basis, not for field work, but rather to lecture on the country's rich archaeology and its traditional architecture. It was during these stays in Oman that I began visiting the country's only remaining wooden boat building yard, located in the historical town of Sur, and not far from the important Bronze Age archaeological sites of Ras Al Jins and Ras Al Had. I therefore turn now to a documented case study of experimental archaeology. The case illustrates the importance for archaeologists of adopting a hands-on approach to learning about human skill and ingenuity, and also the properties and performance of materials that were used by our ancestors in making everyday objects. Oman's geographic location and the predictable cycle of the monsoon weather system are key to understanding the close relationship between the peoples of the Southern Arabian Peninsula and the sea. Sailors of the Gulf and the Western Indian Ocean have practiced navigation for thousands of years, making contact and forging trade relations with the civilizations of Mesopotamia and the Indus Valley. They progressively established trading networks with China, India, East Africa, the Eastern Mediterranean, and by the 19th century, the United States of America and England. There is ample archaeological evidence of trade in the Persian Gulf and the Gulf of Oman during the 3rd millennium BCE between Sumer, Dilmun, which was in the Persian Gulf and is located where Bahrain, Kuwait, Qatar, and Eastern Saudi Arabia are situated now, and Meluha, which is the Sumerian name for the location likely corresponding to the Indus Valley, and Megan, which roughly corresponds to Eastern Oman. Ras Al Jins and Ras Al Had were thriving seasonal fishing and trading villages at the time in Megan. They were two of many settlements in the Eastern Arabian Peninsula where a new social and economic order had developed, characterized by expansion of trade, as well as extensive and quite fascinating tomb construction. Settlements at the coastal sites were constructed of stone and mud brick. Buildings were typically rectangular in plan, with multiple rooms and courtyards with ovens or fireplaces for food preparation. The inhabitants of these settlements had shifted from a hunting-gathering existence to fish processing, shell jewelry production, basketry, rope making, boat building, and local and international trading. Growth in agriculture resulted in food surplus, which was stored or exchanged. Metal from inland mines was available for the production of tools, weapons, and ornaments. Goods and wares imported to Ras Al Jins from Mesopotamia included storage jars and notably bitumen, which I'm going to return to. From the Indus Valley came ceramic vessels, and from Iran and Baluchistan came soft stone vessels. The oldest known frankincense burner, dating to about 2500 to 2000 BCE, was found at Ras Al Jins, confirming local use of frankincense. But it also prompts speculation that this precious resin, harvested from the Boswellia sacra tree in Oman's remote Dhofar region, was already being exported at this early day. Mesopotamia imported large quantities of copper for manufacturing agricultural tools, weapons, and instruments. Bun-shaped copper ingots came mainly from Megan, smelted in the northern coastal region of what is now Oman, and transported by caravan to Dilmun, where they were loaded onto ships for Mesopotamia. Ships sailed along the Gulf and up the Euphrates as far as Mari in present-day Syria. Along with copper ingots, gabbro was also shipped to Mesopotamia. This hard igneous stone, formed from the slow cooling of magnesium-rich and iron-rich magma, and found in Oman's ophiolite complexes, was used for making copper mining tools in Megan. In Mesopotamia, gabbro was used by Sumerian sculptors to carve royal statues, such as the one of Gudea seen in this slide. The people of Megan were exporting and importing goods not only by caravan, but also by boat. But what did these boats look like? From what materials were they made? How were they constructed? How were they propelled? And how were they navigated? From 1985 onwards, remarkable findings of bitumen slabs and fragments at Bronze Age coastal settlements, such as Ras Al Jins and Ras Al Had, provided clues to these questions. Prior to the bitumen discoveries, however, historians and archaeologists had relied mainly on cursory information, gleaned from cuneiform tablets, iconography, and ethnographic documentation of traditional sailing vessels to hypothesize the nature of Megan boats. Lashed timber construction has been proposed for these vessels. It's believed that this method was used in Arabia as early as the 3rd millennium. And lashed construction entails tying planks together with ropes probably made from date palm fiber, which is arranged transversely across the boat's hull. Hull framing is largely or entirely absent. The holes made for passing the fiber rope are plugged with wood to keep the lashings tight. An economic use of scarce timber is achieved by fitting shaped planks together like a 3-dimensional jigsaw puzzle. This also helps to restrict their movement when at sea. During the Bronze Age, imported bitumen from Mesopotamia was applied to keep the seams watertight. The most spectacular example of a Bronze Age boat of lashed construction is the Khufu boat, also known as the solar barge, built for Egyptian pharaoh Cheops and discovered at Giza in 1954. It took years to skillfully reassemble this masterpiece of wooden boat building, measuring nearly 44 meters in length and nearly 6 meters wide. Built mainly of Lebanon cedar planking, it displays a shell-first construction technique using unpegged wooden tenons. The ship was built with a flat bottom composed of several planks, but no actual keel, and the planks and frames were lashed together with halfa grass. An alternative prototype for the Megan boats, however, was one made of bundles of reeds lashed together like the solar barge of the Akkadian sun god Utu, depicted on a cylindrical seal found at Tel Asmar in Iraq. And that's at the top of this slide. A 3rd millennium cuneiform tablet from Mesopotamia, now in the British Museum, lists materials ordered for a shipyard. In addition to several varieties of timber, it names different vegetable fibers and goat's hair for making rope, copious supplies of reeds, huge quantities of fish oil, ox hides, and purified bitumen, which was, as stated on the tablet, for making watertight Megan boats. In 1985, archaeologists led by Maurizio Tosi and Serge Cluzio discovered slabs and fragments of bitumen with impressions at Ras Al Jins. The impressions were of woven reed matting, bundles of reed, rope, and barnacles, which indicated the surfaces of sea-going vessels. The bitumen itself was chemically matched to sources in northern Iraq. In 1999, with funding from the Omani government, Maurizio Tosi and Gregory Puzzle headed an experimental project to reconstruct a hypothetical Megan boat. In addition to the available iconography and direct evidence supplied by the bitumen slabs, background research was also made into the construction of reed boats and rafts built by the Marsh Arabs of Iraq, as well as various types of traditional fishing and sailing vessels that were made during recent centuries along the Omani coast. One of these is the shasha, assembled from the midribs of date palm fronds and still used today, but for inshore fishing only. Logically, as a sea-going, cargo-carrying vessel, a Megan boat would have been significantly larger and necessarily more robust. Naval architecture software was therefore used by the archaeological team to create and assess possible designs of a vessel made principally from reed bundles that was capable of carrying a substantial cargo and of sailing into the Arabian Gulf or across the Western Indian Ocean. According to Tom Vosmer, an experimental archaeology approach was adopted by the project, importantly allowing the team to gain further understanding of the materials and to explore the crafting and assembly processes. The objective was not to reproduce the definitive black boat of Megan, but rather to enable the archaeologists to pose new and better informed questions. The skills involved in boat construction in Eastern Arabia are thousands of years old. Techniques would have evolved in response to locally available materials and would have possibly adopted methods imported from the Indus Valley in Mesopotamia. The original tools used for making the Magan boat would likely have been axes and adzes, chisels, wooden mallets, and spikes and needles made of wood, bone, or copper. Guided by the listing of materials on the cuneiform tablet, the approximately 12-meter-long hull of the hypothetical Magan boat was constructed with bundles of reeds lashed together onto which an exterior covering of reed matting was quilted. And you can see across this slide the buildup of the various materials that were used on the hull. The team produced handmade rope from carex fiber and used Omani sources of acacia and Ziziphus spina Christi timber. Bitumen was imported from Iraq and its properties were adjusted with additions of lime for improving dimensional stability and fish oil for enhancing the bonding quality. The vessel was coated inside and out with that mixture, and the exterior was then smeared with mud. The gunnels were covered with hides fixed in place with wooden nails to protect the reed hull from abrasion. On the 7th of September 2005, the Magan boat's maiden voyage was launched from Sur in the hope of sailing nearly 1,000 kilometers across the Indian Ocean to the historic Indian port of Mandvi. Not 30 minutes into the voyage and just tens of kilometers offshore, the boat sank. The boat was lost to the Arabian Sea, but much valuable learning by the researchers had been gained about material properties, craft work, boat building, and sailing a bundle reed vessel. For me, as an anthropologist, an ethnographic approach to understanding how things are or were made is highly appealing. In pondering how our Bronze Age and Iron Age ancestors made things, it's advisable to begin with the ways that people all over the world are still making things with natural materials and with straightforward technologies that are moderated by the craftsperson's body and guided by their perceptual senses and their experiential knowledge. In the Gulf and around the Indian Ocean, the basic kit of boat building tools has remained largely unchanged for centuries and likely millennia. In addition to the axes, adzes, chisels, and mallets used by the Bronze Age shipbuilders, contemporary boat builders in Sur use hand saws, pit saws, and pull saws, wood planes, bow drills, nail pullers, and caulking irons, as well as a variety of measuring tools and plumb lines. The same is true in distant Zanzibar, which had once been part of Oman's empire. I offer some illustrated examples of contemporary methods still used in both places, in Sur and in Zanzibar. For measuring angles, a protractor made of wood with a weighted string attached is used. For fitting irregular edges of planks together, in the manner described earlier for the Bronze Age boat builders, a simple marking gauge is used. Some kinds of boats are still built plank first, meaning that the hull is assembled first and the framing fitted afterwards. Nails holding frames to planks are clenched on the inside over the frames. In some places in the Western Indian Ocean, like Zanzibar, the carbon steel nails and spikes, as well as many of the carpenter's basic tools, are made by local blacksmiths. Planks are shaped by a kind of steam bending method, which involves bracing the ends of the planks to a stake and twisting them with torque created by tying them to poles. The steam needed for shaping the planks is created by using slow-burning, low-heat charcoal and periodically dousing the planks with water. The charcoal surface of the timber also improves water resistance and rot resistance, very importantly. Alternatively, planks may be shaped with an adze, requiring considerable hand skill and perceptual judgment. Trunks of trees are carefully selected for their curved and V-shaped geometries, as well as for their grain pattern, and then further shaped with the axe and adze to produce the framing that is fitted into the plank hull. A manually operated bow drill is used for pre-drilling holes in the planks and the framing elements through which the nails are driven. Using a mallet and caulking iron, the joints between planks and the individual nail holes are tightly packed with cotton soaked in shark's oil. Like any craft, problem solving is at the heart of boat building. Problem solving activities are involved at every stage of the creative design and making of a boat, including, for example, calculating its dimensions or intuitively engineering its structure, configuring its geometries, the proportions of its parts and its scale, choosing or producing mixtures such as the bitumen coating on Megan boats, selecting and evaluating materials like the reeds, fibrous threads, and leather hides that were used, and modifying tools for the various tasks involved in a making and in assembling. While physically engaged in designing and making, the body of the craftsperson has its own challenges to overcome. At a motor level, they must resolve how to take up good posture, form correct grasps, coordinate bimanual activities and practices, exert appropriate pressures, and perform fluid, rhythmic, and economic movements. They must also resolve how to continue working when injured or when ailed by illness or with aging. The nature of all such challenges and the search for their solutions are timeless, shared equally by our Bronze Age ancestors and by future generations of craftspeople. Paired with problem solving is making mistakes. Making mistakes offers the starting point for learning and improving, as I came to understand as an apprentice on building sites and as a carpentry trainee in London. Learning arises in identifying that a mistake has been made, understanding it as a problem for which a strategy to remove it or resolve it can be devised, and testing the strategy in real practice. Notably, these procedures of learning do not necessarily unfold in a neat linear manner or as discrete events. Rather, the process is messy and dialogic. The relevant point here for archaeologists is that learning and discovery are not confined to abstract thinking about the problem, one step removed from the physical activities of implementing a solution. Instead, learning, whether it's in craftwork, anthropology, or archaeology, demands situated perceptual experience and physical activity, as well as emotional engagement when confronted by a challenging problem, or while working one's way through it. Perceiving, doing, and feeling are all part and parcel of the same cognitive matrix for problem solving, which also includes producing inner dialogue, or interactive dialogue with fellow craftspeople about procedures and discoveries. Importantly, the cognitive matrix also includes the imagination. In relation to boat building, the maker's act of imagining extends beyond his or her picturing what the vessel will look like to include imagining how it will relate to the bodies of its sailors, to its cargo, to changing conditions at sea, and to sometimes treacherous shorelines, as well as imagining how it will be interacted with, moved over land, launched, sailed, navigated, and moored. These ways of knowing and imagining constitute an abundant overlapping exchange of information in the proactive search for potential problems and their solutions. In summary, if discovering a mistake or identifying a challenge offers a starting point for learning, it then follows that the process of learning through exploration, experimentation, and reflection brings about new knowledge or new ways of getting to know something. Like the original boat builders of Ras Al Jins, the archaeologists of the Megan Boat Project will also have discovered this. Experimenting with hypothetical reconstructions of long-lost objects offers a unique and valuable window for sharing, at some level, the conceptual, perceptual, and emotional experiences of our ancestors. It also allows researchers to attain a richer understanding of what it is to be human.
So thank you very much for this wonderful introduction into craft and boat building. And we decided to have only short, there are many questions, okay. Short questions directly to the topic, and all the what we can say about general ideas about craft for the final discussion. Please raise again your hands, because I think, here, Trevor is here, wonderful. And who wanted to ask a question? I saw Aideen, I saw Tryphon. No? Lena? No, there is time for 1 or 2 questions, and then we go beyond, please.
So it was hand clapping, I think, in most cases, actually.
Okay, wonderful. So in this case, because we are rather late, Trevor, will you be with us also for the final discussions, or do you have to leave?
No, I'll be happy to join you.
Oh, wonderful. So we can have the general topic, because
yeah, sure,
that's everything.
Fine. And just to confirm, what time are the final discussions at?
They should be at roundtable at 11:05.
Okay, well, I'll be with you all morning, so that sounds good.
Wonderful.
That's perfect.
Great.
Thank you. Thank you very much.
Thank you.